Hello there. Welcome to a problem session, another problem session in a magnetic field in matter. So this is a very classic problem where you have a very long cable. So you have inner conductor and you have outer conductor. So this is inner conductor and this is outer conductor. And so current goes one way in the inner conductor and then over there comes back there. This thing is continuing, and this guy is also continuing. So you can consider this to be very long, and the space between them is space between them is filled with some material, and that's the linear material. And it could be anything, but these are all conductors. You could have, for instance, like oxygen. Oxygen will be a non-conductor, oxygen gas, and then that will be like something like 1.7 times 10 to the power minus 6, and this will be paramagnet. So if you have an air between them, you can think of that as oxygen, and you can use this value, for instance. Okay, so we want to know what is the magnetic field. So basically we want what's at an arbitrary point, what is B around here. Okay, so you already because there's a material here, we can't use B dot dl equals mu naught I enclosed. This is not correct anymore. So in the material, you can, this is the polarization and this is magnetization. So the material will be magnetized, and so this won't be the correct. The correct laws will be you can write in terms of H, for instance, this field. Instead of B, you write H, and that takes into account whatever the magnetization is. Okay. So when you work out the formula for it, instead of B dot this one dl, this becomes H dot dl equals to this is the freely flowing current only. Okay, enclosed, and instead of mu naught, it's there is no such thing anymore, because that's taken into account by bringing mu naught over here. Plus, you have to take care of this D field, ddt. This is called displacement field of its flux, the D field, if present. The D field will be present if there is a polarization in the material or electric field, right? Or both. But here we don't have that, so in our case this is not there, so we just have this law. Instead of that law, we have this law. So we find H. So once we find H, we can't find B unless we have M. Well, turns out in the linear material, defined by this, that M is equals to chi M H. So if chi M is positive, magnetization in the same direction, chi M negative, magnetization in the opposite direction. So like for dimagnets, like these guys, this guy, magnetization in the opposite direction to what the H direction would be. And for these guys, magnetization would be in the same direction as H. So if you had oxygen, magnetization will be in the same direction as H. Okay, so find H this way, and this is the M, so add them and we get a P. That's our strategy. Okay, so how are we going to find H? So we look at free currents. So we have inner conductor and then we have outer conductor. So we completely ignore all the materials, right? For getting the edge, looks like we can ignore material. If this is magnetized, if the material is magnetized, okay, so just looking at the free current, so it's just an Ampere's law for H. So if the current is going this way and current is going this way over here, we can assume the current is only on the surface, assuming the current is on the surface. So let me write this down. Assume I is at the surface only for these conductors. Okay, so if you had a rod, I just suffer nothing in the middle. Okay, so we're going to assume that. So for this, clearly we need a cylindrical coordinate, right? So this is going to be my z-axis, and this will be the s direction, distance s. So you can say I need to do current going that way, then I'm going to go in this loop in that direction. So the left hand side, by using this symmetry, the field will be, so H will be some H value times phi hat direction. Okay, so this is the phi hat direction at any point, and from symmetry H will be the same, and that will be 2 pi s H, the left side, and the right side will be how much current is enclosed, and the current is enclosed over the surface. The entire current is I, so the H is simply going to be I over 2 pi s, and from here M will be chi m I over 2 pi s phi hat. So from here B will be whatever I got for H, let's call mu naught. The H will be just I over 2 pi s phi hat plus this guy. So you can see I can take out mu naught 1 plus chi m I over 2 pi s phi hat. So that's the answer for 1. It's pretty easy to get the answer, right? Using the H field, the auxiliary field. Okay, and if you have a linear material, this usually turns out pretty easy. You know, if you haven't studied this and this thing shows up in the test, you might be like, wow, this is a hard problem. But actually, if you studied it, this is almost all the problems using H that we can do in a test time are usually very trivial. Okay, let's try to do this. How much did the material get magnetized? Suppose you had oxygen will be actually become magnetized. So how much is the magnetization? Okay, that's very easy to answer right away, right? So we already answered that also along the way. So this also answered. So answered 1, answered 2, both of them answered. Suppose I have a magnetization. This is not in the question, but you could ask, could we have gotten this by using like JB and KB? Can we get these bound currents from M and then use this free current and bound current to get B? So because del cross B is still true, mu naught J all, okay, plus epsilon naught mu naught dE dt. This is always true. So here this is not there. So could we get B directly from here if I can J? So J all here will be J all here will be J free plus J bound plus J from polarization. Now because the material is not polarized, this is 0. So just using these two, could we get B through this equation? And the answer is yes, and you get the same answer. So let's try to do that out in the rest of the video. Okay, so using this law, when you integrate it, you will find, in this case, of course, this is 0 because no polarization. So we just have to enclose, find actually there's a mu naught missing, so there's a mu naught here, so mu naught like that. Okay, so all I have to do is go back there and try to apply this. All right, so if I go back there and so this is against the z-axis, and so this distance is s, and I go in this loop at distance s, the b dot dl on the left side is going to be 2 pi s b along the phi direction, which is the phi component of b, right? And so that's equal to on the other side mu naught free current is I, so this all of the I is enclosed. And how do I get bound current? How to determine this? Bound current will come from this in this formula, but when you integrate it, you're going to be current from all these sources. So let's find out what the I be enclosed will be over this entire area, how the bound current is. So bound current will be only in this material. So that's integral. So we need to know JB from, say, JB is going to be symmetric around 2 pi. So 2 pi JB at S, 2 pi S ds is the area, and it's going to from A to S. What will be JB? JB will come from del cross M, and M is in cylindrical coordinate, so it probably is better to write del cross M and write del cross this is some constant. Some constants say let's call it oh no, write the whole thing, 2 pi I. So this is constant times 1 over S phi hat. So this is just a chi m I over 2 pi del cross 1 over S phi hat. So this is a vector whose phi component is 1 over S. So when you do the del cross of this will turn out to be 0. So you do it in cylindrical coordinate. What you would get is the phi hat component will be S times 1 over S ds. It's going to work out like this, and so that's go to 0. Okay, I will not work out that. You should work out yourself. There's going to be 0. So Jm, so this is going to give me 0. However, if you look at this inner surface here, all these surfaces, actually the n hat is coming down from the inside of the material into outside, this outside of that. So n hat is coming down. So if you look at, so n hat is minus s hat, okay, and we do m cross n hat, will be some, all of this, so chi m I over 2 pi s at s equal to a. I'm at the surface A, and I have a phi hat cross s hat. So if you know, you have a s phi z in circle, right? So minus s hat, so that just gives z hat. So this gives this stuff times z hat. So there is a current at the surface, but this is surface current, so I need to add to it this circumference times the surface current. So circumference times surface current. So this together, this surface current we just found out with m cross n hat is chi m I over 2 pi a times 2 pi a. And so this 2 pi a kind of cancels out. So this I enclosed will, for the bound current, will be chi m. So this mu naught coming from here. So mu naught chi m I. And let me erase this so that I can write it clean. So B phi is mu naught I over 2 pi s 1 plus chi m, and this is the phi component, so the B is mu naught 1 plus chi m I over 2 pi s phi hat. This is the same as before, right? So you can do it two different ways. You can just find the m, then find all the currents, and then go out and do the Ampere's law for B. Or you can just not find all the currents, just work with the flowing current and find H, and then from there you can find B using M proportional to H. And because that's in the linear material, that's M is proportional to H. Okay, that's it's pretty interesting. You know, two different ways we did the same problem, and I hope you enjoyed it. If you like these kind of explanations and these kind of problems, please hit the like button. I appreciate if you have some feedback to me, some comments, something like that. I always try to respond to it. If you haven't subscribed to the channel, maybe you want to subscribe it so that you can be reminded when I put some new material on. You can check out my website. Okay, take care. Bye.